Helion's fusion generators use two fuels to make electricity, helium-3 and deuterium. Deuterium, a form of hydrogen, is a naturally occurring element that comes from any large body of water, like oceans and lakes. And our oceans have a lot of it, enough to power all of our current energy needs for billions of years. And helium-3 is a form of helium that also occurs naturally, but it's extremely rare to find it here on Earth. However, we can make helium-3 by fusing deuterium and deuterium together. As we do fusion, our systems will produce 5 byproducts as a result: a proton, helium-3, helium-4, tritium, and a neutron. A proton is a nucleus, or the core, of a normal hydrogen atom. We can capture a proton as electricity. Helium-3 is recycled back into the machine and used as our fusion fuel. Helium-4 is a safe gas, the same kind of helium you would find in a party balloon. After a year of doing fusion in a 50 megawatt generator, you could fill about 3,000 balloons with it and have a really fun party. Tritium is a low-level radioactive material with a half-life of 12.3 years. Our systems capture tritium, then we filter and store it in secure containers. As it decays, it turns into helium-3, which we use again as our fusion fuel. So the tritium that we make is really useful to create more of Helion's fusion fuel. This container could store all of the tritium produced by a 50 megawatt generator in 1 year of doing fusion. These containers can be safely stored as the material decays into our fuel. Our systems will also produce a neutron. A neutron has no electric charge, so they can't escape the magnetic confinement of our generator. We halt them in their path using thick concrete shielding walls. We add other materials to the concrete, like boron, so we can catch as many neutrons as possible. The radiation from neutrons does create low levels of activated materials over time. We've specifically designed our facilities to only use materials that would result in a manageable amount of activated material. And we add fire suppression systems to prevent any accidental release of such material. Fusion machines do not generate high-level radioactive waste. This isn't to say they don't produce radiation or radioactive material at all, but they have a similar radiological footprint to a hospital where X-rays and MRIs take place.
Helion's pulsed fusion device directly recovers energy, which is used to generate zero-carbon electricity from fusion. It starts with Helion's fusion fuel, deuterium and helium-3. These fuels are injected as a gas into Helion's formation chamber, where they are superheated into an ionized gas called a plasma. The machine's capacitors are charged and send electricity to magnets that wrap around Helion's device. The magnets invert the plasma's magnetic field on itself into a toroidal, or donut shape. This type of plasma confinement is known as a field-reversed configuration. The electric current inside of an FRC flows in a loop, generating its own magnetic field which confines the plasma. FRCs are formed at both ends of the device. The device's magnets fire sequentially, accelerating the plasmas toward each other at a velocity greater than 1 million miles per hour. They collide in the fusion chamber and merge to become one hot, dense plasma. In the center of the device, the machine's magnetic field is rapidly increased, compressing the plasma with a powerful force over 10 Tesla. Due to the Lorentz force, this increase in field compresses the plasma smaller and smaller, increasing density and pressure until the plasma reaches temperatures exceeding 9 kiloelectron volts, equal to 100 million degrees Celsius. At this temperature, many atoms overcome their electrostatic repulsion of one another. This allows the atoms to get close enough to each other for fusion to occur. All these fusion reactions within the plasma convert matter into new energy, which strengthens the plasma's magnetic field. As the plasma's magnetic field gets stronger, it pushes back on the magnetic field of the machine, causing a change in the machine's magnetic flux. In accordance with Faraday's law, this change in flux induces current in the machine's coils, which is directly recaptured as electricity and returned to the capacitors that originally charged the magnets around the machine. This whole process occurs in a millisecond and is repeated in a pulsed manner.
So Helion's approach to fusion use a deuterium and a helium-3 fuel. Deuterium is really common. It's 1 part in 500 in all water. It's in the coffee you drink. And safe and readily abundant and low cost as well. We buy it in compressed gas cylinders. It's already purified, but you could imagine doing the purification yourself. It's pretty straightforward. The helium-3, however, is ultra rare. And in fact, while helium-3 was theorized in the early days of fusion as being the best fusion fuel, because of its rarity, there haven't been a lot of approaches that have used helium-3 or demonstrated helium-3. To our knowledge, Trenta was the first system we know about that did bulk deuterium helium-3 fusion for a power generation application. One thing Helion has done is we patented a helium-3 process of creating helium-3, of taking 2 deuteriums found commonly in nature and at high pressure in a fusion system, ironically, fusing them together to form helium-3, taking one more deuterium, fusing that with the helium-3 to make helium-4, and that's what makes the electricity.
So it's only the reaction of the deuterium with helium-3 that generates the...
The deuterium with the deuterium generates some amount of electricity, a small amount. It generates about 1/8 of the deuterium helium-3 reaction.
What influences that?
So what influences the amount of power output per reaction is the actual atomic physics that's happening, where when 2 deuteriums combine, they have a few reactions, but the one we care about most will create a helium-3. And that helium-3 will have a lower mass deficit, so the amount of missing mass of that final product. So E equals mc squared, and that mass deficit is the amount of energy that's released in terms of the particles that are created and their temperatures. And so deuterium helium-3 has a larger mass deficit when it forms helium-4, and so you end up with more energy trapped in that helium-4 as well as in the other proton that is made.
2 types of fusion can occur when fusing 2 deuterium atoms. One creates a helium-3 atom and a neutron. Most of the energy of that fusion event is carried away by that neutron. Tokamak reactors generate electricity by converting the kinetic energy of neutrons to heat in their walls. But Helion's energy capture system can't generate electricity with neutrons because they have no charge. Helion needs charged particles to push back against the magnetic confinement to generate electricity. That neutron just flies right through the magnetic jail. The helium-3, however, carries about 0.82 mega-electron volts of useful energy that the generator can capture. In a second possible reaction, deuteriums can create a proton and a tritium, with the proton carrying 3.2 mega-electron volts of energy and the tritium isotope carrying 1.01. Helion's generator will capture as much energy as possible from these particles before exhausting them through the turbomolecular pump in the diverter section, with the protons regaining an electron and becoming hydrogen, and the radioactive tritium being transferred to remote storage. Here, it will beta decay into helium-3, but this process takes 12.3 years to occur. When it finally does decay, that helium-3 can be fed back into our generator. So, Helion has 2 pathways to create helium-3 for their primary fusion energy reaction. When deuterium and helium-3 combine, they create a helium-4 atom and a proton, releasing 18.3 mega-electron volts, more than the 17.6 mega-electron volts released from deuterium and tritium reactions. And on a mass basis, 4 times more than a uranium fission reaction.
Gérald Jonas, qui avait construit la première Z-machine aux États-Unis en 1976. Et moi, j'ai pu voir cette Z-machine à l'époque, en venant aux États-Unis.
Et vous avez pu constater qu'il y avait des températures extraordinaires.
Non, on ne s'y attendait pas, justement. C'est là que c'est extraordinaire. Il faut que les gens écoutent ça. Parce qu'une grande découverte scientifique, ça se produit par hasard. Quand vous faites passer un courant de plusieurs millions d'ampères dans ce cylindre, par exemple en cuivre, à ce moment-là, il a tendance à imploser. Mais il implose très mal. Le courant se tortille et on n'arrive pas à faire marcher un compresseur MHD. C'est de la MHD, bien sûr, un truc comme ça. Et alors, il y a un Russe qui s'appelait Smirnov qui a eu une idée. Il s'est dit, mais pourquoi on ne remplace pas le cylindre par des fils? On va faire une cage avec des fils. Alors, on a fait une cage avec 140 fils qui avaient le diamètre d'un cheveu. Dans chaque cheveu passait 70 000 ampères, vous voyez. Et alors, à ce moment-là, il s'est passé un truc incroyable. C'est quand on a fait cette expérience, Ces 140 fils ont réussi à converger vers un truc qui avait la taille d'une mine de crayon. Et on a une température de 2 milliards de degrés qui a été obtenue. Personne ne s'y attendait. Pourquoi? Quel est le paramètre qui a fait que ça a fonctionné? Le paramètre, c'est que le courant a été délivré en 100 nanosecondes, c'est-à-dire un dixième de millième de seconde. Et à ce moment-là, quand c'est l'équivalent à un courant de haute fréquence, alors les gens qui ont un peu de notion de physique qui m'écoutent savent qu'un courant haute fréquence, il ne circule pas dans le conducteur, il circule à la périphérie. Donc autrement dit, les 70 000 ampères ont circulé dans le cheveu, mais l'âme du cheveu est restée solide, ce qui a permis à ces choses-là de se concentrer. Alors je me rappelle, Jonas a dit, qu'est-ce que c'est que cette histoire, 2 milliards de degrés, je veux faire des mesures. Alors les mesures, on fait ça par un système à élargissement de raies, peu importe, on a construit la machine, on a refait l'expérience, ça a confirmé, on avait bien fait 2 milliards et même 3 milliards de degrés. C'est énorme. Alors tout de suite, moi j'ai percuté là-dessus en disant, mais si on est capable de faire 1 milliard de degrés, on est capable de faire la fusion bore-hydrogène. Le bore, il y a 11 nucléons. L'hydrogène, on prend l'hydrogène ordinaire qui en a un. On fait l'addition 11 et 1, 12. 12, ça fait 3 héliums. Donc c'est une fusion qui produit de l'hélium. Et je me rappelle, dans une bande dessinée que j'avais faite dans le temps, j'avais cité cet exemple de cette fusion aneutronique en disant, effectivement, il y a quelques neutrons secondaires, mais le déchet, c'est de l'hélium, vous vous rendez compte?
Donc un déchet tout à fait inoffensif.
On peut gonfler les ballons des gosses avec, vous vous rendez compte?
Et ça produit... L'énergie produite est colossale.
Mais bien sûr, c'est l'énergie de fusion. Et alors, il y a aussi une chose, c'est que dans ce système-là, on a compression et puis on exploite la détente du plasma.